All right, let's take a look at 12.2. So we're going to look at transformations involving powers, roots, and logs to create a linear model that is, it describes the relationship between two quantitative variables. So it makes it linear. So essentially what we're doing, and you can see it here, is we're going to look at this graph and it looks like it is not linear. So the form is curved. So what today's lesson is going to be is how can we straighten this relationship out so that it looks linear and we can use it to make predictions. So just quickly on this data, this is showing the life expectancy of people from the whole world. These are the different countries, or this is the continents, and each dot represents a country. And this is the income per person. So you can see that as income per person increases, the life expectancy increases as well, but up to a certain threshold because it is curved. Now, the different size dots is just because they're showing the population size as well. So the larger dots are larger countries. So since this relationship is curved, one way that we can straighten a relationship is right here. They took the logarithm of income per person. So instead of just showing the income per person, if they took the logarithm of all the x variables or x values, then re-expressed it and life expectancy stayed the same, this looks much more linear. And so this is just to show you that we can transform scatter plots just like we did with other distributions. So there's two models that we're going to be looking at. The first one is called a power model, and power models are whenever we have x raised to a power. So when x is raised to a power, or that's what it looks like, then we are going to be using a power model. And when we're working with power models, there's two ways that we can transform power models. The first way is raise the values of x to the power of p. So x to the power of p, whatever the power is. It could be x squared, it could be x cubed, or x to the fourth. The second way, and you don't do anything to y, the second way is you can take the pth root of the response variable. So take the square root of y, or the cube root, or the fourth root, whatever it is, to make the data look more linear. Now, usually, and today especially, I'm not going to have you actually do the re-expressing. You're not going to have to actually raise all the x values to some power or take the square root of the y variables. Let's take a look at an example. Imagine you have been put in charge of organizing a fish tournament in which prizes will be given for the heaviest Atlantic Ocean rockfish caught. You know that many of the fish caught during the tournament will be measured and released. You're also aware that using delicate scales to try to weigh a fish that is flopping around in a moving boat will probably not yield very accurate results. It will be much easier to measure the length of the fish while on the boat. What you need is a way to convert the length of the fish to its weight. You contact the nearby marine research lab, and it provides reference data on the length in centimeters and weight for the Atlantic Ocean rockfish of several sizes. Here's the scatter plot of the data. Note the clear curved form. All right, so here's the scatter plot they were just referring to. You can see it's positive, it's strong, but it's curved. So since it's curved, the transformation made the association roughly linear because we used computer software to perform a linear regression analysis of weight versus length cubed. So what they did is they cubed all of the lengths. So you see here, 5.2, they would have cubed that. 8.5, they cubed it. They cubed all of them and then replotted the data, and it looked more linear. I don't have an actual graph of the re-expressed data. This is the original one, but I have the regression output. So here you can see the output, and it tells you it's showing the weight versus the length cubed. So you need to look at this output to figure out what did they do to transform the data. And they tell you here that length was cubed. So the slope is going to be the coefficient of the x variable length cubed. So here's our slope. Our y-intercept is the coefficient of the constant. And so the equation for the least squares regression line would be the weight with a hat. It's very important they have the hat because it's predicted. 4.06 we said was the y-intercept, and the slope is 0.014, blah, 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 right there. So really this first thing is just writing an equation based on the computer output. Next, suppose a contestant in the fishing tournament catches a rockfish that's 36 centimeters long. Use the model to predict the fish's weight. So now they're telling us that the length is 36, so x is 36. We're going to plug 36 in for the length and get the predicted weight. So plug 36 in, cube it, do all the math, and you get 688.9 grams. So this is just like what we've done before. The only difference is now we're using transform data to make these predictions and to write out the equations. So this is one way they could have transformed the data. They could have cubed the length, which they did. Another way, and I do have a graph down here actually. Here's what we just saw. They cubed all of the x variables, and you can see this graph was a lot or much more linear, and it labeled length cubed down here. The second way we could do it, like we discussed at the start, is we could take the root of the y variables. So if you look here, they took the cube root of the weights and then re-expressed it. And this also looks linear. So we're going to do the same thing, but now using this new transformation. And it tells you, here you go, we took the cube root of weight versus length. Length stayed the same. Here's our output. So write the equation for the least squares regression line. This right here is going to be your slope, the coefficient of the x variable, and the y-intercept will be right here. And there you can see it. So you still have the cube root of the weight, and you need your hat because it's still predicted. Y-intercept, slope. What estimate will we have for a fish that is 36 centimeters long with this model? So you're going to plug 36 in for length again and solve. So plug in 36, multiply it by this, subtract this from it, you get 8.856. Well, remember with algebra, if you have the cube root of x is equal to 8.856, you have to cube both sides. So that's why they cubed it to get 694.6 grams. And so let's see, the last one was 640 or 688. And this one was 694 grams. So they're pretty close. Both of these models are pretty close in their predictions.